So today we are going to go through maximum principle with subject to some inequality constraints. And these inequality constraints I will mention to you in the next slide. They are definitely very important for any kind of problems that we have in management science. And the maximum principle that we're going to use is going to be kind of based on what we did in chapter 2 in the last lecture, but we're not going to prove the whole thing. We're going to some kind of give some rationale of why what we're doing, and it will sort of draw upon our knowledge of the proof in chapter 2 and our knowledge of calculus and math programming, and those things are going to come in there. Okay, Lagrange multipliers, for example. So given all those things, we're going to put it together and eventually come up with the maximum principle, and then we'll apply the maximum principle to several problems. So that's kind of the idea here. So first set of constraint is just a constraint on the control problem. So at any time t, the u, which is the control variable, satisfies this inequality. Now, this constraint is not much different from what we did in chapter 2. In chapter 2, we still had something called u in omega t, and omega t was the constraint on u at time t. But all we are trying to do now is to put that constraint in an inequality format rather than in a set membership format. Okay, mathematicians usually like the set membership format, but the people who do optimization, they prefer inequality format because it lends itself to the math programming kind of connections. The second kind of constraint is when x is also involved. So when both x and u are involved, these are called mixed inequality constraints. Even though this one doesn't have x, we can leave that as together with this. It doesn't make too much difference. Okay. But there's another kind of constraint where u is not there. This is the constraint only in terms of x. And what happens is in the control theory, we change x by changing u. That means we have a differential equation, which is dx dt, and the right hand side has some kind of function of u. And so when we make u, we create x dot, and then when we integrate, it gives us x. That means that we cannot directly change x. We can only change x by changing u. That indirect way of changing x makes the problem much more complicated. So our plan is to do these constraints, treat these constraints in this chapter, and treat this constraint called pure inequality constraint in chapter 4. Chapter 4, as I mentioned to you, is the most complicated in terms of theory, and theory is still developing in some sense because it is a difficult problem. And so we will defer to this kind of constraints until the next lecture. So let's just state our problem. We have a habit of stating our problem in a general setting, in a vector kind of setting. But when we do the proofs and whatever, we kind of think of everything as scalars. And if we need to change into vectors, with appropriate putting transpose here and there, everything goes through. So it's better to think without burdening ourselves in terms of many dimensions, but we need to at least specify the problem. So the specification of the problem is we have x. X is in n-dimensional space. U is an m-dimensional space. That means there are n state variables and there are m control variables. And there's a function that takes all of these guys, which is en cross em cross e1. E1 is for t. So that function that is taking an element in this cross product area to En, which means x dot. So if I apply this to f, if I apply f to this thing, I get x dot. X dot is again n-dimensional. Okay, so that's sort of how we define the differential equation. Same thing, we have an objective function, which is a function of x u t, but this objective function is not n-dimensional. This f gives you one-dimensional. That means it is a number. This will give us a number because it's profit. It's dollars, let's say. So we integrate those dollars that come every instant. We integrate that from 0 to t. And when we end up at a t is our terminal time, we take the salvage value. That means we have some state. Ut doesn't really matter because EU is going to be only at one point, so it doesn't contribute anything. But xt is a state. It's a state variable versus a flow. So that is a system at that time, and there's a value that can be associated with that. Now, I think Kai was last time asking a question about discount factor. We will do the discount factor in this chapter later. But this t right now is very general. That means if I want to put a discounting, I don't have to put it outside. It is just a general function. So everything is included in this specification of that function. Let me also mention to you that t can be fixed, or t can itself be a control. That means I can decide the time of t. So if t is fixed and given to us, then of course we don't need to put this t. It doesn't mean anything because we are given. Only the value of x at that t is important. But sometimes the t is something that we need to decide, in which case that t is there. So I like to keep this like this, even though when t is fixed, you know that this is just sitting there for convenience of notation in some sense. Okay. So this is the objective function. It consists of a rate of profit, let's say, that we want to integrate, and then it consists some value of the end at which time, if there's a company, the company plans up to t period, then it should say something about what happens to this company beyond t, and that is implicit in this thing. Okay. Of course, if t is infinity, we don't need this because there is nothing beyond infinity. Although that is also not correct. Mathematically, there could be something in a limit, but generally in the practical problems, you won't see anything when t is infinity. There is no salvage value. So once again, we specify constraints. This constraints is, it basically says, is it Q here? Q means there are Q such constraints. So I have a function, and when I apply this G to this, I get a G1, G2, GQ. And this is equal to 0. That means I have a Q different constraints. I could also put a constraint at a terminal value, like xt bigger than or equal to 0 would be one example. That means my wealth cannot become negative, or my inventory should not become negative. Then I could say xt bigger than or equal to 0. Then that's a constraint. I can also say that I leave the system with xt equal to 0 or wealth equal to 0. I don't want to have any wealth after t. I want to consume everything, let's say. So this could be equal to 0. So you can have two kind of constraints. I'm now saying that constraint A, there are L sub A constraints, and B, there are some L sub B constraints. These are the number of constraints. So that's a dimension of how many constraints there are. That's the dimension of how many constraints there are. So we now have a problem. We have a state equation. We want to decide on control and possibly t to maximize this, subject to some constraints, these constraints. Now, I just want to mention to you that mathematics people sometimes prefer to have a more general setting. A more general setting is a set. That means xt is in a set yt, which we specify. And yt has to be a subset of xt because xt is all the possible states that we can reach, given those. That's defined by all the possible states we can reach from initial value x0 and applying any control that is feasible, any control path that is feasible given all of these guys, then that will give you the set xt. And certainly any constraint that we impose has to be a subset of that. Otherwise, if you put xt bigger than this, it is not effectively not constrained because that's all we can do anyway. Well, sometimes, like if this was a simplex, we can write that as a set of inequalities. But if it is more complicated, then this problem cannot always be written in this form, because this says that I can convert that to set by a set of finite inequalities or equalities. For example, take a circle. Suppose yt was a circle and xt was a two-dimensional variable that lies in that circle. Well, I need infinitely many linear constraints. Infinitely many linear constraints to describe a circle. And so that's not completely undoable, because you can develop a whole theory to say that I allow infinitely many constraints. And if you allow infinitely many constraints, then more or less you can replace this by that, although not quite, because if this was sets that were not connected, there were more complicated version of the set that you cannot write as an equality. But anyway, we're not gonna be dealing with this kind of stuff. Most of the constraints that we will deal with be of this form. Okay, so for example, we will be dealing with xt as an interval. Let's say interval, let's say -1 to +1. You can write that as this set because that's an interval, but you can also write that interval this way: xt bigger than -1, xt bigger less than +1. So you can write that in two different inequalities. So that most of the stuff that we're going to be dealing with this, but I want to just tell you this just so that we have a connection with them. Okay. These are conditions needed for existence of an optimal solution. And I don't want to tell you too much about where they come from. And there is a whole course that one can do on existence. And I only mentioned to you in the last lecture that existence is important, because if there did not exist any solution, then you can do anything you want. So every theory becomes basically useless. So we need to put some conditions. These conditions are conditions basically saying that if I have these constraints G, then I would say that when these constraints are tight, that means this is as equality. Then all those constraints at any point that are equality, they should be linearly independent. Okay, and we already had a definition of what is linear independence in chapter 1. And this is another way to write linear independence. That means this will be, so let me just show you what that means. It will be, so the first, so this is derivative to E, so the U is m dimensional. So the first m component will be a row vector with respect to G1. Remember, it's anytime you take a derivative with respect to this, it is a row vector. So there will be a gradient of G1. Then the second row will be a gradient of G2. The third will be a gradient of G3, and so on down the line. And then this will be a diagonal matrix. So it will be G1, G2, G3, Gn. So you can see that only one of these will be active in this row. So this row will be m rows. Then there will be q rows here, and there will be a q rows this way and a q columns this way. There will be m columns this way. So this will be m plus q versus q. So m plus q by q matrix, and that has to be equal to q. So that's basically allows you to say that they are linearly independent. Same thing works here. I have inequality constraints. So if it's inequality constraint, I have put a diagonal matrix. If it's equality constraint, then it's 0 anyway. So you don't need to worry about the diagonal matrix of B. And then that all set of constraint has to be equal to the LA sub LB, which is the number of dimensions. And that will again give you a linear independence. Okay, so this is all we need to talk about here. And we need to go and define our problem. So we have now this problem to solve. We maximize this subject to this equation and this constraint. And of course, we believe that some of those conditions that we just replied are satisfied by these G's and A and a B and all of that. Okay, so that we have existence. We don't ever need those other than when we derive the conditions necessary and sufficient condition, we need to have some existence. So that's all we need that for. So as before, as in chapter 2, we define Hamiltonian. So Hamiltonian is f, which is the integrand plus some adjoint variable lambda times the right-hand side of the differential equation. But now what happens is we maximize. Remember in chapter 2, we maximize this Hamiltonian. And we proved that maximizing maximum principles say that this Hamiltonian must be maximized at each point in time. So we want the same thing happen. But now this Hamiltonian has to be maximized subject to this constraint, subject to these constraints, this constraint. And so there we apply the theory of Lagrange multiplier or theory of math programming. The math programming says that if you want to maximize this Hamiltonian subject to the constraint called G bigger than or equal to 0, then I put a Lagrangian. Okay? This Lagrangian applies to this Hamiltonian. Okay? It is not the Lagrangian of this problem, although people would still say Lagrangian, but it is the Lagrangian of this problem. At each point in time t, I have to maximize the Hamiltonian subject to some constraints. So I have to maximize this by doing a Lagrange multiplier. But Lagrange multiplier usually is when you have an equality constraint. But if you don't have an equality constraint but inequality constraint, then this Lagrange multiplier is more complicated. And from the math programming classes that you took, either from Millen or you will take later, this mu has to satisfy something called like complementary slackness conditions. So let's just quickly relate that to our Lagrange multiplier. If G equal to 0 was the constraint, if the constraints were all equal to 0, which is a special case of this, because every equal to 0 constraint can be written as two such constraints. So suppose I have a constraint G equal to 0. I can write that constraint as G bigger than or equal to 0 and minus G bigger than or equal to 0. So by writing those two constraints, I basically write a constraint G equal to 0. That's why I don't put G equal to 0 as a separate constraint here, because that allows enough generality for us. We don't need equality as a separate. Some people do it. Some book may do separately, because then they will have to write a mu1 and a mu2, and then mu1 will satisfy different conditions. Okay? So if G was equal, then what happens is that this will always be 0. So I don't have to put any constraint on this. But if G was bigger than or equal to 0, then I need to put this constraint on that. So that's called complementary slackness condition. It also means that if G was strictly bigger than 0, suppose at some point this G was strictly bigger than 0, then this mu is equal to 0. Because if it's bigger than 0, then this mu has to be equal to 0. That's component wise, okay? So suppose G1 was strictly bigger than 0, then it turns out that essentially that constraint is not tight. That means if I change U, it's not going to make that much difference because I have enough slack. I'm an interior solution. Because I'm an interior solution, there's no need of Lagrange multiplier. So that mu becomes 0. So that's where the complementary slackness comes in. and it has some intuitive notion of what is going on. And it was proved by the math programming theory for this kind of thing was proved by Kuhn and Tucker. And so you call them as Kuhn-Tucker conditions of math programming. Now, so this is where we are now deviating. We had a lambda dot that was minus delta h delta x. And you remember that we derived the lambda by maximizing the Hamiltonian. We kind of we said it by maximizing Hamiltonian with respect to x at each point in time, given u star. That was a proof of deriving the equation for lambda dot. But now we're maximizing Lagrangian. And so it would appear reasonable the lambda dot would be minus L sub x. So delta L delta x of the Lagrangian. Okay, so this is a change. Then in the previous chapter, lambda t was just this. It was the derivative of the salvage value because we didn't have any constraints on the terminal variable. But now there's a terminal variable constraint, so the lambda t will get some multiplier from the terminal constraints. So we need multiply alpha and beta. Again, because this is bigger than or equal to 0, so we need this kind of complementary slackness conditions, and this b is equal to 0, so we don't constrain beta at all. Beta can be anything. It could be positive or negative. And why it can be positive or negative is very clear, because if I for example here, if I take something equal to 0, I write that as g bigger than 0 and g smaller than 0. And g smaller than 0 becomes minus g bigger than 0. So I have two, I would put two multipliers. One is mu1, one is mu2. And it turns out that when you put them together, they come together as mu1 minus mu2. And the mu1 is bigger than 0, mu2 is bigger than 0, but mu1 minus mu2 can be anything. So that's why we don't need a constraint on beta. Okay, so anytime you have an equality constraint and you apply the multiplier, then the multiplier is unconstrained. Okay, so that's a general theory from math programming. Also can come from a even more general theory of duality, but we are not going to go there. So, as I mentioned to you, I'm not going to prove it, but I give you an idea of how you got there, some ideas, and the fact that we had a maximum principle for a simpler problem that we actually proved. We can now write the necessary condition for u star a trajectory to be optimal. So if u star trajectory is optimal, then first of all, corresponding x star, which is the trajectory obtained by u star, will satisfy this differential equation. And clearly the x star t that we obtain by using this has to satisfy the terminal constraints. Clearly lambda dot satisfies our constraint of the maximum principle. Lambda t, which is terminal value, must satisfy this. Again, alpha should satisfy at complementary slackness condition. Then the Hamiltonian must be maximized at each point in time. But to maximize the Hamiltonian at each point in time, subject to this constraint, we maximize Lagrangian. And we maximize Lagrangian, we don't actually maximize Lagrangian. We take the first order condition of Lagrangian. In order to maximize the Hamiltonian, we take the first order condition of Lagrangian, which is delta L delta U, U at U star T. I think this should be equal. It is equal, I think, in the book. It just doesn't show equal when it is smaller. And so that is equal to, you take the derivative, the derivative by definition of L is this and this, and that's equal to 0. And the complementary slackness conditions hold. So there's a lot of conditions to verify. But that is our maximum principle. Any question here? Because we're going to now apply this to several examples to get some more sense of what is going on. Okay. Let me not spend too much time on it because most of the time we will not need that, but you need that also to complete the theory. If x star t was in a set like that, then the terminal condition will be like this. It is almost like a complementary slackness condition. Either lambda t is equal to this or y is on the boundary. So something like that would give you the condition. So that one, it is possible if you can express yt in terms of a and a b, well, sorry, in terms of these two guys, and it's possible for some yt. If you express that yt in terms of a and b, then this equation will allow you to derive the conditions we derived earlier. So I think this is in some exercise in the book that start from there, derive those conditions. There will be a table later on that we will list all those conditions later. So let's hold on to that for a while. This is important. What if t was a decision variable? If t was a decision variable, let t star be the optimal solution for that. Then we need an extra condition which says that Hamiltonian must satisfy this condition. If t star was an interior solution with 0 and infinity, certainly t cannot be less than 0. So the only space for t is between 0 and infinity. And if t was 0, that's a trivial problem because it means no problem, right? If you optimize an optimal solution is t equal to 0, then that is not a practical problem that you want to solve. Although you can have mathematical stuff to come to something like that. So we need an open interval on this side, and certainly infinity is not a number, so it's always open on this side. But if t star was, if this was finite, then we need to put some math programming type conditions on that. We will do that later. So that is a condition. One way to look at it this way is the following. One way to derive that is to solve the problem for any given t. Okay? If you solve the problem for any given t, then the objective function j, this will be function of that t. Everything else will be gone because everything else will be part of the optimal solution. So the entire function of j will be a function of t. It may not be easy to specify that function explicitly, but implicitly it is a function of t. And how would you maximize j of t with respect to capital T? It's just the one variable. You need basically a first order condition of calculus, which is dj dt equal to 0. So this exactly, if you do all of that, then you can prove that dj dt equal to 0 will give you this. I'll talk a little bit more about it. I'll also give you a reference to understand more if you wanted to understand more. But if we are going to apply that, then we can use this condition. Okay, so this is our recipe. This is our recipe when t is fixed. This is our recipe when t is not fixed. Okay, so this is what we can use as a recipe. So now the first problem is this problem. T is fixed at 1. Differential equation is given as t. And here's our g. G can be written as two constraints, u bigger than 0, x minus u bigger than 0. It could also be written as a set, and the set is u is in interval 0, x, where x is whatever it is. Okay, x is endogenous. Okay, but whatever x it is at that time, u must be less than that. Okay, this is the condition that we have. So let's use the recipe. The recipe says Hamiltonian. Okay, so we build the Hamiltonian. And we need to maximize the Hamiltonian. So this is linear in U, so the maximizing of Hamiltonian is simply 0, x, 1 plus lambda. That says that if 1 plus lambda is bigger than 0, U star will be x. When 1 plus lambda is less than 0, U star will be 0. And if 1 plus lambda is equal to 0, I can set anything I want, at least if it is just at one point. And if it's not at one point, then it's a singular problem, and we keep talking about singular problem in terms of time to time, but that means that if it's only at one point that this quantity becomes 0, then it doesn't matter what you set U at. You can set it 0, you can set it x, you can set half x, you can set whatever you want. But if this is more than 1 point, then you want to maintain that at 0. And maintaining that 0 will define U, because there's certain U that will maintain that to 0. So while it is arbitrary at single point, if it's an interval, it is not arbitrary anymore, because condition will come out of maintaining this at 0. And that's why it's called a singular control, because that's a singularity of this function that has to be maintained. And there's a lot of theory of singular control. There are books written on it, the whole book's written on singular control. But we will get more examples of that, more beautiful examples of singular control when we come to applications. We have a Lagrangian. Lagrangian H, we have two constraints, G1 and G2. This is the second one. This is the second one. So I have a mu1 times U and mu2 times x minus U. Okay, so those are the two constraints. And this can be written that way. Once again, so now what happens is I will get lambda dot. Lambda dot is minus mu2. If you take the derivative of this, you see the derivative with respect to x only gives you mu2. So it is minus mu2. And lambda 1 equal to 0 because we have no terminal condition here. So the derivative of s will be 0. And we have no terminal condition on x itself, so the multipliers will also be not there. So altogether, it's a simple problem where this will be 0. And first order condition of Lagrangian must be satisfied. And mu1 has to be bigger than or equal to 0, mu1 u equal to 0, mu2 bigger than or equal to 0, mu2 times x minus u equal to 0. These are the complementary slackness conditions that have to be satisfied. So what we have gone so far, we applied the recipe to this problem, and after applying the recipe to this problem, we have certain conditions. And we need to now figure out how to find the control that satisfies these conditions. Well, it's not that easy right now because we don't know mu2. So what we're going to do in this, again, while we're trying to show you necessary conditions, we're trying to show those on examples that are simple and their solution can be easy to guess, okay? More complicated examples will come later. But it's clear that I'm going to maximize this. And U is between 0 and x. So it seems reasonable that the optimal control U will be equal to x, because x is the maximum value I have. And as I apply the maximum value, then this will only increase. And if I apply more of it, then it will increase faster. When it increases faster, again, I put U equal to x, so that will keep increasing. So clearly, U equal to x will be an optimal solution. So this is very simple case in this case. And now we want to kind of use this idea that the U star t is xt. Okay. So all we're now going to do is to see if all the conditions are satisfied. Okay. Because necessary condition must be satisfied on an optimal solution. So we want to check that. Well, initial value is 1. u star equal to x. So I can put x dot equal to x, x dot equal to x, and that is the easy solution, exponential solution. When x dot equal to x equal to e to the t. Because notice easy. If x equal to e to the t, then x dot is also e to the t, so x dot equal to x is satisfied. And at 0, it is 1. So this is solution of that. Once I have a solution of that, then I know that this is bigger than 0. It's strictly bigger than 0 in most places, except one point, so we don't worry about that. If it is strictly bigger than 0, then u star is bigger than 0. So you see this condition, this is satisfied with strict inequality, and this is satisfied with equality, right? So we know this is satisfied with strict inequality, which means its multiplier will be 0. And this is satisfied with equality, so its multiply can be bigger than equal to 0. Okay? So we know mu1 will be equal to 0. So mu1 will be 0. And mu2 we don't know. It can be whatever it is. But we know from the first order condition of Lagrangian that if mu1 equal to 0, then mu2 equal to 1 plus lambda. If mu2 equal to 1 plus lambda, then 3.19, right now I can go back and forth because it's not far. I now can write lambda dot equal to minus 1 plus lambda. So this equation now is a differential equation in lambda, and I can solve it with the boundary condition lambda 1 equal to 0. So I can solve this equation like this. Lambda t is e to the 1 minus t minus 1. It's a linear equation. It's easy to solve. You can solve by integrating factor, or you can use the formula in the appendix to solve it. There are a number of ways to solve that, but it is the simplest differential equation that you will learn if you ever took a course on differential equations. If you took a course on calculus and had a chapter on differential equation, this is what you will learn. So the u star x satisfies the condition, but now we have a mu2 because mu2 is 1 plus lambda. 1 plus lambda is e to the minus 1t, so mu2 is 1 e to the 1 minus t. So this is 0 and mu2 is 1 minus t, and it is bigger than or equal to 0, so it is satisfied. So complementary slackness condition is also satisfied. We want to make sure that this is bigger than 0. So it is. I'm now going to make a number of remarks. These are only there so that if you read chapters and if you read control theory books, which are more mathematical, then you may not be surprised. So I put some remarks. Mathematics people actually define Hamiltonian like this, and then say that this vector is not equal to 0. But if lambda 0 is 0, then the problem is meaningless because the objective function f is nothing there. And so that's called, so most of the time lambda 0 will be bigger than 0. And when it's bigger than 0, I can normalize it to 1. And so in our book, we always assume lambda 0 equal to 1. Problems where these things happen are pathological problems. In literature, they call our problem, they call normal problem, and anything that is not normal could have a lambda 0 equal to 0, and so much for that. Okay, so those are not the problems we are interested in. Because the Lagrangian function is a Lagrangian Hamiltonian and not the Lagrangian of the original problem, some purists don't want to call it Lagrangian. They call it extended Pontryagin function. Okay, so I'm not going to do that. I'm just going to keep it as Lagrangian. And most of the books do that. But there are those who don't want to do that. So be it. Fourth remark is this is an interesting constraint. I can have a fixed constraint That means I want a solution so that x star t is exactly equal to k. If we apply that to our condition, it will tell you that if this is fixed, then the lambda that is associated, no, the beta which is associated with x star t will be a constant to be determined. So the lambda t will equals to a beta. Beta is a constant to be determined. Okay. And of course, if x star equal to k, there is no meaning of salvage value. Because salvage value is just, this x star t cannot change. So this cannot be a function of something that cannot change because it's a constant. And so S is not necessary, but lambda t becomes beta, which is to be determined. And remember, you solved two-point boundary value problem using Excel. You had initial value of x0, and you guessed the value of lambda t. And then you asked the Excel program, the goal-seek algorithm, to find that value of lambda 0, initial value, that will give you lambda t exactly equal to 0. That was the final value of lambda t. So if I gave you x0 and also gave you lambda t, let's say lambda t was 0, then there's no freedom anymore, right? Because I have x0 and I have a xt, and then I have a lambda t. So I cannot satisfy all of them. So it's natural for mathematics to have something that is reasonable, and it turns out that the theory tells you that the beta is constant to be determined. So I have a two-point boundary value problem where I'm given x0 and I'm given xt. But now I'm not given lambda t. So how would I solve this problem in Excel? I will solve this problem in Excel by starting with x0 and starting with lambda 0. And I run the program all the way. And then instead of saying goal seek so that lambda t is 0, I would say goal seek so that xt equal to 0. And that will give you the new guess of lambda 0. And with that new guess of lambda 0, x0 will be x0, xt will be k, lambda 0 will be whatever was given to you by the algorithm, and lambda t is whatever it comes down to. Because both lambda 0 and lambda t are free. So they can be whatever they want as long as we can fix x0 and xt. So two-point boundary value problem still works. The Excel program will still go through for this kind of problem. As before, lambda it is the derivative of the value function. I just want to say that this is the marginal value only as long as the derivative of this value function is defined. Remember when I did in chapter 2, I said that we don't have the right to say that this is differentiable because this is a function we want to derive. And we proved the maximum principle assuming it's differentiable. So the proof of maximum principle was only good for those values where value function will be differentiable. So it's not completely rigorous proof, but that's all we can do. But we can still find some problems where value function is not differentiable, and at those points it is not differentiable. Lambda it would not have a meaning of marginal valuation because there is no derivative. And there's something more involved, which I don't want to talk about right now. But there is a maximum principle when this is not differentiable, and then lambda does not is not v sub x, because v sub x is no longer a number. When vx is not differentiable, vx is not a number, it is a set. It's called a set gradient set, and this lambda then belongs to that set. So all we can say is the marginal value belongs to this. It has a lower bound and upper bound, so the marginal value is somewhere between the lower bound and upper bound. But that's just, we don't do this in this book. All we are going to say in this book is that when this is not differentiable, we don't have a marginal valuation, at least as far as we are concerned. What is alpha I? Well, the alpha I is a Lagrange multiplier which is associated with this constraint AI, and it is a value of the resource here. That means suppose I change this to that. Notice when I change to that, I can only reduce the objective function because that constraint allows me more x trajectories than this one does. And if I allow you more trajectories, then I can get a better objective function. So first thing we know is that when I do from here to here, if epsilon is positive, then I can improve the value of the objective function. If epsilon was negative, then I can decrease the value of the objective function. I cannot improve it. And so the marginal valuation is minus epsilon times alpha I. That means the value function will suffer by this amount, an order of magnitude smaller than epsilon, which we can always call 0 in most cases, as epsilon goes to 0. So that is the marginal valuation that gives you the approximate value of the new objective function. One more remark is that sometimes these terminal constraints are binding at the very end. When it's binding at the very end, then this lambda t is really the left-hand limit. So it is actually lambda t minus, the lambda t minus. So what I'm trying to say is that in general, we don't do that here. We will do that in chapter 4. But in general, this should be lambda t minus. In general. Okay. And if that's the case, then lambda t without the minus is exactly this. Because if I give you a value exactly at t, then the marginal value is given by s sub x. Salvage value, take the derivative of the salvage value. Sorry. Take the derivative of the salvage value, and that will be exactly lambda t. That is exactly at t. But at t minus, it is given by what is in the box. Okay. More. What is the meaning if I change this constraint by this? Well, this constraint by this is a little bit more complicated because there's a mu I which I apply to this, but these are not constrained at f. These are constrained on a trajectory. That means at every t. Whereas that constraint was only at t. So it has a more standard value of the marginal valuation. This one is a little bit more complicated. And because it's on the trajectory, the entire trajectory now has to be bigger than epsilon, not bigger than 0. So I suffer the loss in value function. But because it has different t, I get little bit of a value at each t, and the total value has to be integral. So the total value will be minus epsilon times 0 to t mu I t dt, integral. So this is the marginal valuation interpretation of mu. So mu has an interpretation in this sense. Okay? Last remark. And this remark is there in this book only because in the chapter in economics, I give the optimal control theory that is needed to derive the mechanism design when time is continuous. Somewhere along the line in your courses, you will learn mechanism design, which is a problem when information is not symmetric, and the theory of mechanism design require optimal control theory when the state is continuous. And that theory requires something where the constraints are on the initial condition. And so you can basically change the whole stuff. You can consider the reverse time. So this T becomes the initial condition and this becomes the final condition. And the entire theory goes through. And you can read the remark, because the entire theory goes through, you can write conditions this way. And the reason I put this remark is because I will need these conditions in that chapter in economics when I develop mechanism design. So that's the only purpose for this remark. You already know this. If D is a convex set, I define a function on a convex set. It's a concave if, like this. It's a concave function is a function like this, so that if I join the line 2 points on a function, then the line is underneath the function. Okay, so the function is above the line. This is the line joining 2 points. Okay, 2 points y and z. When I join the line of 2 point, this is the line, and this is the value at any point on the trajectory on the function, and that is above the line. Okay, so that's the general definition of concave function. Quasi-concave is when it's the minimum, it's bigger than the minimum on those 2 points. Difficult to draw this kind of function, but that is a mathematical condition. If it is strictly convex, then this is strict inequality. And if a function is convex, then minus psi is, if function is concave, then minus psi is convex. So by defining a concave function, strict concave function, and a quasi-concave function, I have also defined convex function, quasi-convex function, and strictly convex function. Okay? And I do that because I need this definition in sufficiency conditions in this chapter. Here's the sufficiency condition. I'm now going to define a maximized Hamiltonian. So here's a Hamiltonian xu lambda t. I'm going to maximize this Hamiltonian subject to this constraint, gxu2 bigger than or equal to 0. You know, that requires the Lagrangian condition and derivative with respect to tu and all of that. But there's a maximization, and the maximum argument that will give you the maximum, let it be called, we can call whatever we can call. At some point we call u0, u0 to be the function that will maximize this. That u0 is going to be a function of x and t. So when I put u0 as a function of x and t, we did that in chapter 2 when did the sufficiency condition. Then this function becomes a function of x lambda t. So that is the maximum of the Hamiltonian for any given x lambda t. So now the sufficiency condition like this. Let x star, u star, lambda, mu, alpha, beta satisfy the necessary condition of the box 3.12. If this is concave in x, that's why we define the concave function. In xu, concave in x, g is quasi-concave in xu, a, which is the strict inequality, is quasi-concave, and a b, because it's strict, it's an equality. So an equality can be expressed as two inequalities, and one is quasi-concave, one is quasi-convex. So this has to be linear. Any function that is both concave and convex would have to be linear. Okay, so that's linear, then x star u star is optimal. So this is our sufficiency condition of chapter 3. This is where we come to discounting. Okay. Was it Kai that asked that question last time?
Yes, yes, it is
Okay.
hard.
So now let's now go through very carefully what is going on. Now this function, if I have a discount rate, I'm going to write it that way. Notice I don't want to put t here, because if I want to put t here, it already sufficiently general, so I don't need the discount rate. So what I'm trying to now say is that the only way this t appears in this objective function is via the discount. There is no other dependence on t, because if there were any other dependence on t, there is no value of putting discount rate outside, because that already contains that. Do you understand that part?
Yes,
You don't need to put t here anymore. So the only value of discounting is if I can write this function this way, where the dependence on t is only via this factor and not any other way. Because if any other way, this doesn't give anything more. There's no need to change the formulation. We just go to the standard formulation and use the standard formulation. Okay? Similarly, sxt can be written as some function of psi x e to the minus rho t. So I now have, instead of f, I have a phi, and instead of s, I have a psi, and I have a dependence on t is given by this. So my objective function now is given by this. So far, so good?
yes, so far so good.
Now I want to derive the equation for lambda and the value function for this problem. Okay. So first, in order for me to define this and draw a distinction between the previous formulation and this formulation, I need to have some extra language. So first of all, the previous formulation is a present value formulation. There was no discounting. There was a dependence on t, which could be whatever it is. It could even be discounting, but the formulation would be present value. So the present value formulation of HPV, if I do what I did in chapter 2, then chapter 2, HPV will be f plus lambda times f, right? Small f. F is e to the minus rho t phi xu in chapter 2. And even chapter 3, earlier part of chapter 3, that would be HPV. The HPV is f plus lambda fx ut. So that's the thing that we already did. But the reason I put PV on there is because most of the book we will use discounting, because that's business problems. You need discounting for future cash flows, right? Generally speaking. So because we need discounting, we want not to put too many subscripts for problems of discounting. So what I want is, I want the Hamiltonian, current value Hamiltonian without this PV. I have two ways to go. I can call the previous Hamiltonian H and the new Hamiltonian H of CV. CV means current value. Or I can redefine the previous Hamiltonian as HPV and the current Hamiltonian simply H. And that's what I'm going to do. I'm going to define the current Hamiltonian to be H, which is coming. We don't have it yet. But the previous one that was H is now redefined to be HPV. Okay? So HPV can still be defined. Okay, question.
So can you explain in English what is the difference between present value and current value?
Yes. So let's go back here. You have a book. Let's go to the book first. Let's go to chapter 2. And I want you to go to exactly. I want you to go to 2.9, page 33.
33. 2.9.
Okay? Everybody has it? Equation 2.9 on page 33, which is the definition of the value function. You see it?
Give me 1 minute. It's 33.
Page 33 in the book.
2.9. Yeah, I see it.
Okay. So you see the value function from t to, it's integral from t to t.
Yes.
Okay. That value function is a present value function. That means, so let's go a little bit slower on this one because it's important. Suppose I put t equal to 0, small t equal to 0.
Okay.
So that's the beginning, okay? If I
Uh-huh.
put small t equal to 0 and small x to be x0, which is the initial value,
Uh-huh.
then the v of x0 comma 0 is exactly j star. That is the optimal value of the objective function at time 0.
Yes.
Now I am at t. So at small t, the value function is still at time 0. It is
Yes.
a problem at t, but the dollar values are at time 0. So it is in the present value sense. So even though the problem is being defined at small t, which is in future, the
Uh-huh.
v of x comma t is in the dollar at 0 value, zero time dollars. You know, dollar has an inflation or discounting, right? So I can have a dollar at time 0 and a dollar at time t. So dollar at time t has a value e to the minus rho t times 1, right?
Yes.
So even though I have a value function at time small t, I can evaluate that value in terms of dollars at 0.
Yes.
So that vxt is dollar at 0. It's a VPV. If you want to put PV on that, that is VPV. V
Okay.
superscript PV, okay?
Okay.
So I have a Hamiltonian PV also because this is, notice now, that one at time t is still a value at time 0, right? Because it is discounted by e to the minus rho t.
Yes.
So when I define this, this is a Hamiltonian at time 0. It is Hamiltonian at time t, but the value is at time 0.
Uh,
Got it?
I got some sense, I think.
Okay, because see, Hamiltonian is given as xu lambda t, right? So
Uh-huh.
that HPV is still a function of xu lambda t, right?
Uh-huh.
It is a function of xu lambda t, so there's a t inside there in the argument. But I put PV, it means there is a value is being evaluated as a zero time dollars.
I
Dollars
understand.
at time 0. So present value means dollar at time 0. Current value means exactly the dollar at time where you are at. So small
Uh-huh.
t is the current time.
I
0 is the present time.
uh-huh.
Present value is different than a current time. Current time is where I'm at. So
Mm.
I am at time small t. Okay, so that is the current time. And I'm evaluating the value of the Hamiltonian in present value dollars. Okay,
I understand.
so the
Thank you.
Lagrangian is in present value dollars. And the lambda dot now is in a present value kind of dollars. So all of this is the chapter 3 earlier part, right? We just applied the box. This is the box that we 3.12. We applied 3.12 to this problem. This problem. Going back. Let's go back quickly. Oh, sorry. So we have this problem where F and S are there. We apply the maximum principle to this problem, which is this box. Okay? We now want to use this box for the special case of this problem, where F is given by e to the minus rho times phi, and S is given by e to the minus rho capital T times psi. So I give a special case of this problem. I apply this theory to the special case. Okay? So I get exactly these equations to the special case. So when I apply all of that, I get this. You can go to that box 3.12, and one by one, you will write this. Got it? Now
Yes.
I'm going to convert. Now what I'm going to do is I'm going to define the current value version of these guys, which is the next slide. So now I'm going to define the Hamiltonian like this. You notice I don't put e to the minus rho t anymore here. Did you see that?
Yes.
See, this is different, right? Here's the e to the minus rho t. Here's lambda PV. Now I'm defining this e to the minus rho t, and I put lambda, not lambda PV. Okay?
Mhm.
Also, same, the Lagrangian. And look what happens here. I'm now defining, that is the present value lambda at time small t. But if I want to take the current value, then current value, I have to multiply this present value by e to the rho t. Look at this way. This is the current value. If I want to bring that current value to the present value, then I have to multiply this lambda by e to the minus rho t. If I multiply this by e to the minus rho t, I can bring the e to the minus rho t on this side, and I get this equation, right? This identity. This is a definition. So now I brought that dollar, which was $0, zero time dollar, to t time dollars. This is the t time dollars. Okay? Same for mu. And same for h, right? And same for L. So this lambda, this h, this L, this mu are current value dollars at time t. So as t changes, the current valuation is in terms of that t, where the present value is always at 0 regardless of what t is, right? Now, once we have this lambda, I can do lambda dot. So I take the derivative of this lambda, I get lambda dot, and lambda dot is easy to do. And lambda dot PV I already have from here. It's from here somewhere, right here. So I can write that. And when I do all that, it's easy translation. I get this.
Professor, I have another question. So from present value to current value, it's kind of like a reverse engineering. So you just multiply e to the power rho t. So I was thinking this is based on an assumption that t should be some finite value, right? So what if we want to make the terminal time go to the infinite?
Oh, that's later. Later. Let's don't worry about that right now.
Okay.
We'll get to that later. But that is a big T, not small t. You're talking about big T going to infinity.
Yes, yes.
Right now, small t doesn't go to infinity. Small t is current value. So we are at any given time t, and that t is any given time t. And so at given time t, I can see what is going on. Okay. So when I do this lambda dot, I get this, I get this. All of these are standard algebraic calculation. And I am now, instead of 3.12, I have a 3.42. Now this box is in current value formulation. It's called current value maximum principle. It is no different from 3.12, except that the dollar values now are given in current value dollars than the present value dollars. Okay, so if the discount rate is 5%, then you know the 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 rho is the rate of discounting, and the reverse of rho is the rate of interest. So if I have a $1, then and a rho is the rate of interest, then at time t that $1 will become e to the rho t dollars, right? Which is the same way as saying that if I have a $1, if I want a $1 at the current value, how much dollar do I need at the beginning? And that will be e to the minus rho t dollars, right? So that's one is just the opposite of the other. So we now have a formulation. So let's look this way. These are now new variables. Okay, we don't, once we apply this, we don't worry about lambda PV, HPV, whatever. Everything now is self-contained. So x dot is this given, a and b are given. Lambda dot is, this is the big change. You see the change here? I now have a rho lambda which was not there in 3.12. So this is one big change. There's no change here. There's no change here. There's no change here because you maximize is positive. E to the minus rho t, e to the minus rho t is a positive number. So you maximize, if you maximizing this is maximizing this, same, right? Because e to the rho t is positive and it doesn't depend on control, right? So you can maximize h or maximize HPV is the same thing. So I maximize h and I have all of this. So the only thing that changes is this. Everything else is the same. There's more of it. Later on, we will go to the value function. You will see a little bit more. We will derive, where am I now? Yeah, sorry. We will derive, we will see a little bit more about this later, okay? But right now, it is a straight transformation of going from dollars at 0 time, which is the present value. Present value is when the time begins, and at any time t we are at. Because as time goes by, we are at a different time. So the $0 becomes the past in some sense. So these are the same. Now you see that condition 3.4, that condition 3.42, not 3.4, the maximum principle. But there is a condition which is given for when the t is still a decision variable. You will see that condition that comes here after the 3.12. Yeah, it takes a lot of time to go back to these things. So here's the condition. If t is also a decision variable, you need this condition. You will see this also change a little bit. So when we go to 3.44, you will see there's another term coming in there. But that's all, again, straight algebra. You can go one from the other because you know how to convert one from the other. This is the conversion formula. You see, this is all the, this is the conversion slides. So you can, everything here is one-to-one mapping with everything prior to that. So you see there's another term coming here, rho psi. So this is a difference, and this is the difference. So if you want to do current value, you don't have to go to 3.12. You can just do straight away 3.42. What we did is derive this 3.42 from 3.12. We derive this. Once we derive this, we can just use this. So you notice now, I don't want CV on this H because I'm going to be using this a lot. So I want lambda to be without CV and H to be without CV. And that's why for this chapter, in order for me to make that, I needed to redefine those guys as PV. This is different from the previous edition. It's an improvement in some sense. Okay. Somebody has to holler whenever you need a break. Now we apply the current value maximum principle. So we apply 3.42 to this problem. We now to maximize the utility of an agent. The utility is given by log of C, and I'm going to discount it. So this is the utility given at time t, and this is discounting. So the present value of the utility that I want to maximize is given by this formula, and then there is a when my wealth is zero, this is zero. Zero is not time zero. This is the W. So when W is zero, because WT is zero, this is the bequest value of B0. So if I have no money left, it's a bequest value, okay? I do it to just give some meaning to this zero, because later on I want to make this zero into a W. So I want to have a different wealth that people leave. So you think about this as a person who has certain beginning, a person who has a wealth zero, W0. With this wealth, the person wants to consume and derive this utility. And this utility he wants to maximize. And he wants to maximize in such a way so that he doesn't leave any wealth at the end. And when he doesn't leave any wealth at the end, he may want to uh, uh, consider some utility. But if t is fixed, this is fixed, that this is just a number. It does not change the objective function problem. I'm doing it only because later on I want to connect this to another problem, okay? So this is right now a constant. Maximizing this integral is same as maximizing this plus that constant. So this individual maybe has no children. He doesn't want to leave any wealth to anybody. And he just wants to consume and live like there's no tomorrow, okay? And so he's going to maximize, and we're going to use the maximum principle now. Just note that you don't want ever a negative wealth, even though I'm not putting any condition on W small t. That means along any path, WT, I'm not putting any condition. It's a state constraint, which is chapter 4. I don't want to put any condition. But you know that this individual cannot go bankrupt. Because if he goes bankrupt, then from then on, he cannot consume anything. And if he cannot consume anything, then he will be a log zero. And log zero means minus infinity. So there is no way he's gonna have his wealth go to zero. So another way to say is that if I want to consume my entire wealth and leave nothing, then I will make sure that this means this satisfies at every t. Okay. In fact, it will be strictly bigger than zero at every t except at capital T. But I make this remark because we will come back to this remark again. This problem is going to stay with us all the way to chapter 13. But it's going to become more and more complicated. At some point, it becomes stochastic. So keep this problem in mind because it is going to be staying with us for a long time. So the individual has a wealth zero. He keeps his wealth in a savings account, and the savings account earns the interest at R. So while his wealth is earning an interest at R, he's consuming. So the W dot is RW minus C, because this is the rate of interest coming in. This is the consumption going out. So the rate at which the wealth is changing is given by this. If he consumes more than interest, then this is going down. If he's consumed less than interest, then this is going up.
Excuse me, Professor. Did you just mention that in the objective function, the bequest notation, there is a tempo or something?
No, it's not a typo. What I'm saying is that in this problem, the wealth is required to be zero.
Yes.
So the argument of bequest will be zero, right?
Oh, yes.
So B0 is a constant because I cannot get any other wealth.
Oh, yes.
So you can say, okay, if I leave zero, I am so happy that I will call myself that I've done well, and I will give myself back on a thank on my hand. I give what is called a slap on my back, and I call that to be B0, and I will discount that. But it's
Oh,
constant. It is constant, so it doesn't change the optimization problem. Okay, but
oh,
later on, I want to connect this to when it is not zero anymore. Okay.
it's kind of if it is not zero, it's kind of like B, capital B. Then in the parentheses, it should be some the rest
Yeah.
value.
If I'm free to leave wealth, then I will make it W.
Oh yes,
But
yes,
right now, I'm making sure that I'm not going to leave any wealth.
yes, yes.
Fixed
I,
endpoint problem.
I see. I see. Thank you.
Okay. Hamiltonian, no problem. Now this is the current value Hamiltonian. Remember, I don't put e to the minus rho t anymore. See, this is gone. So I don't put that anymore. But while this is gone, this comes in its place. You see that? So that is the price you pay. To simplify Hamiltonian, I have to make the lambda more complicated. There's no free lunch, okay? So that's lambda dot. Notice this is a fixed endpoint problem. Because a fixed point problem, lambda t is a constant to be determined. It has to be free, okay? So what is the solution? Well, the solution of this equation is easy. It's lambda t equal to this. So once I have that solution, I maximize the Hamiltonian by first order condition. I take the derivative with respect to c. I get 1c minus lambda equal to 0. So c equal to 1 divided by lambda. But I already know lambda, so I can put 1 divided by lambda, which is this. Once I have c, I can put c in there, in here, in here. It's a function of time, so I can solve this problem. So I can find wt. So here's a w dot t. I solve this, you get w star t. So I have the wealth trajectory, consuming optimal, but it is a function of beta, which I don't know yet. So I'm going to make sure that when I put capital T here, this is 0. So I put w star t. So I get c star t, w star t. But what I want to do is I make w star t equal to 0, and I determine beta. So here's w star t equal to 0. This gives me beta equal to this. Then I substitute this beta in c star. I get the c star t and w star t. So I consume this rate. I get the wealth at time t. My objective function is given by this. I add b0 at the end because I need a b0 to end there. And my lambda t is given by this. This is the current value adjoint function. If I want the present value, I multiply this by e to the rho t. And that will give me the chapter 2 and early chapter 3 object lambda. Or see time t dollar? You see time t dollar? This gives the margin value per equivalent at time t in time t dollars. There's time $0 and time t dollar. Time t dollar is the current value dollar. Time $0 is the present value dollar. Okay? This is, I think we should take a break here because this is um, quite a bit of doing here. So we will take a 5-minute break, okay? And we'll come back.